live, and then we start. Hello, everyone. Welcome to our new episode of our machine learning security seminar series. I'm Maura Pintor from University of Cagliari, and today we have as host, as guest, Jérôme Rony from ÉTS Montréal, who will present his work on a general framework for white box attacks, adversarial attacks. Just a few things before we start. The event is live streamed and recorded. So first, if you are in the Zoom call and don't want to be recorded, please join the YouTube live stream. Otherwise, feel free to stay in the call, and at the end, we will give you a chance to ask questions. As for asking questions, you can ask them either in the Zoom call, which will be prioritized. Also, you can ask questions during the talk, so you can also raise your hand, and we will give you time to ask the question directly. Otherwise, you can type the questions on the Zoom chat, and last priority, but still at the end of the talk, we will also ask questions from the YouTube live stream as comments. Also, feel free to follow us on Twitter or Eventbrite to receive updates on new events. And lastly, let me thank all the people that helped me organizing this seminar. Now I'll give the stage to Luca, who will present our speaker for today. So good morning, everybody, again. So today we're going to have Jérôme Rony, which is, it's already here. It's from the ÉTS Montréal, where he received his master's degree in system engineering in 2019, and now is currently a PhD candidate at the ÉTS Montréal. And his current research interests include computer vision, adversarial example, and optimization method applied to deep learning. And today he's going to talk about about his findings and his research. So, Jérôme, the stage is all yours.
Thanks. Thanks for the great introduction. So I'll share my screen now. Yeah, it's fine. Okay. Is it working? Yeah.
Yes.
Okay, good. Right. So today I'll talk about, I'll present mostly my last work that we published at ICC, but since I didn't know really what my audience would be, it's more general than just the last paper that we did. It's more of thoughts and facts about adversarial attacks and making a general framework for it. Okay, so first I'll introduce adversarial examples. I think most of the audience know, but still we'll reformulate the problem and everything. Then I'll talk about the problem formulation from an optimization perspective and the constraints that we have, like explicit and implicit, because I think we mostly talk about the explicit constraints from an optimization perspective, but there is actually quite a lot of implicit constraints when making adversarial attacks. There is like a third section that's a very brief literature overview that motivates our last work, and then in the last section I'll talk about our last work, which is Augmented Lagrangian adversarial attacks. So adversarial examples, what are they? First, like everyone knows, deep learning is very good. It's since 2012. It's been getting really good at classification and all visual tasks, but not only visual, semantic, language tasks as well, and so on. But sometimes it also fails. And here is an example. It's an adversarial example. So you have an image X here, and you add a perturbation delta. That is not noise. I often hear the confusion, but technically it's not noise. It's not random at all. And here we amplified it for it to be visible. But when we add it to the original image, which was correctly classified as, if I recall correctly, curly-coated retriever in the ImageNet challenge. We obtained this new image X tilde, which has no visible difference between the two, but this one is classified as a microwave. So that's a bit of the issue. And from then, people started doing adversarial examples for all kind of stuff. So these slides, I mean, this slide and the next one are not from me. They are from the NeurIPS 2018 tutorial on adversarial robustness, which is a really great tutorial if you are interested in that and don't know much about it. But basically, you can create objects that will fool like facial recognition software and models. You can put small pieces of tapes on signs, and it will fool a sign recognition model. And then you have plenty of videos on YouTube of Tesla cars basically going in a wall or just, I mean, just not recognizing the road at all, even though there is nothing special about it. So why do we care? It's because we can argue that this issue is purely synthetic, but there is there are three main reasons that we care about the issue. First, it's the security perspective. So you can imagine that in systems that are that use biometric, for example, authentication, that could be an issue. There is the safety aspect. So like I said, Tesla cars or I mean, self-driving in general. You could have also safety issues in medical diagnosis and etc. And the last point, which in my opinion is what we are, or at least what I am interested in as a researcher, is the issue of ML alignment, because humans fail as well. Like sometimes we fail at recognizing things, and model and deep learning model fail as well. The question is, where do they fail? Like, is there an intersection of these failure modes, or is it disjoint? It's still like a big question, and I think it's, in my opinion, it's one of the more interesting aspects of this issue. So how do we craft these adversarial examples? Because I said it's not noise. So if you take an image, for example, and use the model ResNet 101 trained on ImageNet. So if you take this image of an Aaron, I think, and you start modifying it in two random directions, random orthogonal directions in the input space, and for each modification, you start, I mean, you evaluate the prediction of the model. You get this kind of plots. So here, each color represents a different class. So that means when you add some noise that you normalized, L2 normalized, and you add about 100 times this normalized noise, you get this image. On the first axis. If you do it on the second axis, you get this image. And if you do it on both axes at the same times, you get this one. So you could argue, are they still images of Aaron? It's like there is a debate, like for us humans, but I'd argue mostly yes. But, and the model also agrees on two of the image, but not on the third one. Like two of the images, you can add a Gaussian noise of norm 100, and it's still classified correctly. If you add both perturbations, it's not. But so there's that. But here you added a perturbation that's that has a norm of 100, which is a huge perturbation. But there is a better direction. So if you do the same thing, but instead of taking a random direction, you take the negative gradient of the model, of the output of the model at the original class. You normalize it, you keep the same scale, and you obtain this graph. So it's basically the same as before, but just compressed on the x-axis. And here, if you take if you still add the perturbation in the vertical in the vertical direction, you still get the image that you had before, and it's still classified correctly. But if you add the perturbation that's only five times the normalized gradients, you get this new image, and this one is not classified correctly. And I think we can all argue that this image still looks correctly classified, still look like a heron. And this is what basically sparked all the research on adversarial example, or at least the generation of adversarial example. So now that we have seen how we formulate that, I mean, how we can obtain them, how do we actually formulate the problem? So just a bit of a primer and classification, or at least defining the context. So we have sample X that is in the input space, which for images is basically the 0-1 interval time to the power of D for images, and with the label Y that's in 1K. We have a classifier F that goes from the domain big X to the codomain RK, and parameterized by theta. The prediction of the model is called the logits. And then the logits are normalized with the softmax operator to get the probabilities for each class. And the predicted class is the Rmax, basically, of the probability, which is the same as the Rmax of the logits. So generating adversarial perturbation is can be formulated as a constraint optimization problem, or more exactly as a feasibility problem. So you just want to find a perturbation delta such that the argmax is different from the original label. And to that, you add two constraints. First, there should be, in my opinion, ordered differently actually, but you have the constraint that the original image plus the perturbation is still a valid image. And then you add a constraint that a distance, which measures the size of the perturbation, basically, between the original image and the perturbed image is less than epsilon. And you can choose epsilon. And this problem is usually declined in two ways. You have the minimal perturbation problem, which basically is minimizing the size of the perturbation such that you induce misclassification and still remain in the valid image space. And the maximum loss, in which you maximize the loss such that the argmax is, the prediction is different, and you have a perturbation that's a perturbed image that's less than epsilon far away from the original image. And in my case, I'm more interested in the problems on the left, on the minimal perturbation problem, for the reason that solving this minimal perturbation problem is equivalent to solving the feasibility problem that I presented on the previous slide for every epsilon. So basically, you want to, if you find the minimal perturbation, you found the epsilon for which you can still find a feasible solution to the previous problem. And for any epsilon smaller than that, you cannot find a perturbation. One thing that was missing in the previous formulations is the distance function. Mostly in the literature, this distance function are LP norms. So P and the most studied ones are 0, 1, 2, and infinity. And in the order of importance, it's probably infinity, 2, 1, and 0. Then you can have LP norms plus regularization. So it can be an LP norm plus another LP norm. Oh, there's a missing backslash here. You can have a group, you can add group sparsity to that. It's the structured adversarial attack, I think. You can add some image-aware LP norm regularization. I think Francesco, who is here, can talk about that. and so on. You can add basically a lot of regularization on top of that. And then you can also minimize any function that measures some kind of distance between two images. You have the SSIM. You could use the color difference formula that perceptually measures the distance between colors. The one Wasserstein distance, the Alpibs distance, etc., etc. You can imagine as many as you want. To these explicit constraints of domain and distance and misclassification, obviously, you can. There are also additional implicit constraints. First, F is non-convex, so there are a lot of things that you cannot do since F is non-convex. Evaluating F and its gradient is very expensive. For models, it can go, I mean, you can have a model as small as you want and as big as you want, but typically models like ResNet models are in the 10 power to the power of 6 to 10 to the power of 10 multiply adds, sorry. So it's very expensive even on GPU. Have F as a very high Lipschitz constant as well, and that makes optimization much more difficult. It's impossible to store the Hessian. So the Hessian of the input for 256 by 256 RGB image is 144 gigabytes. So it's not impossible to store it, but good luck storing that on GPU, at least for now. But even if you could store it, inversing it is in cube of the input size in terms of memory, so it's undoable. You have small optimization budgets. Typically, what the community agrees on is about 1,000 iterations maximum. More than that, and it gets way too long, and people will not use the attack that you created, basically. Numerical precision can be an issue, and we have run into that in our attack, actually, because it was getting too close to the decision boundaries, and depending on which GPU you were making the computation on, you would get different results. So since we're doing float 32, which is not precise at all, and finally, the attacks that you make should also work for robust models, because a lot of we have seen it, like a lot of attacks that were working very well for non-robust models completely fail on them, and that leads to a wrong conclusion about the robustness of a model. If you use an attack that is not robust on a robust model, you get incorrect conclusions about your robustness. And one last constraint, I'd argue, is the implementation matters. There is this whole idea that research, a paper should be enough on its own, and that if the idea is good and the implementation is bad, it doesn't matter. And I tend to disagree. First, default matters. So like I said, the attack should be robust, and that means the defaults should be good. And if they are not, there should be clear guidelines on how to actually choose the parameters or the hyperparameter of the attack. And the reason for that is that if you don't have that, people are going to use an attack that was in the original publication. The conclusions were that the attack is very good, and then they use it to evaluate the robustness of a model, and they conclude wrongly that the robustness is very good. But it's just because the attack doesn't work. Obviously, it should run on GPU. It may seem a silly constraint, but I can give you examples of attacks that do not run on GPU fully, and you can see that they are not used at all right now, even though they are very good, but just they are not used. It should be written in PyTorch, obviously. Well, this is just a joke, but I tend to think that it's easier to read after, or at least EagerPy. And finally, one big thing, it should not have bugs. And that's again, that may seem like a silly thing, but there are many attacks that come out that get released with bugs. And here are a few examples of bugs I found. So there was the Kalinin-Wagner attack that had a bug in its original implementation. It's now fixed. The STR attack, there are several bugs in there. It's not fixed. The BNB still has a bug in it. Even though you could argue it's not a bug, it's a numerical precision issue that makes it fail sometimes. The PERC AL attack also has a completely wrong implementation of the color distance formula, which means that the results is terrible. The FMN in its first release had a bug, but it's now fixed. VFGA, which is an L0 attack that has a very interesting approach on doing attacks, but also had a bug and still has one. But the author are in the process of correcting it. So, and that's just the one that I found personally. And there are probably in other attacks, and it's so you can see it's not only one attack that has a bug. And one last point is that, in my opinion, also attack can fail silently, and that echoes a blog post of Andrei Karpathy, which is really great about training neural networks and how they fail silently sometimes. So it means that the code doesn't fail, like it doesn't stop, there is no error, but the performance is not as good as it should be, because there can be any and many issues, and that's a big problem. So now talking about now that we have all these constraints, I'm gonna show a few, like mainly two families of attacks in the literature, and how it and why it motivated our work. So first, there is projection-based attacks. So basically, in these attacks, you rely on the properties of the distance that you try to minimize or try to have to satisfy constraints on. So you rely on the properties of this distance to project the perturbation. And the prime example of this kind of attack is PGD. So you start with your inputs, and you add the sign of the gradient times alpha, and you project it back onto the epsilon ball around your original input. And these methods are usually very efficient. So it can be anywhere from 10 to 1,000 iterations to get excellent results. But the issue is that it lacks generality, because you need to know the projection in order to use this kind of methods. And so it only works for functions with non-projections. So LP norms, one Wasserstein, and that's basically it. I mean, there are probably several others, but at least from in the studied one in the literature. And there is a very large literature of attacks that use this kind of projection-based approach. So you have the FGSM, FGM, iterative FGSM, PGD, default DDN, sorry, FAB, and so on and so on. There are dozens of that. The second main family of attacks is the penalty-based attacks. So instead of solving a constraint problem, you transform it into an unconstrained one. And that's mainly the approach of the Carlini and Wagner attacks. So you minimize the distance plus C, which is your penalty weight times your penalty. And here it's a differential of logits. It could be other things, but it works pretty well in practice. So it's more general with respect to D. In this case, since we're using gradient descent, you only need D to be differentiable. The issue is that it's usually inefficient because you need to find the optimal C with a linear and binary search. So if your C is too low, you're not going to respect your misclassification constraint. And if your C is too high, you're going to obtain a perturbation that's very large because it respects too much your misclassification constraints. And here, that's a plot that we presented in our first work 3 years ago. It's the plot of the optimal value of C for all the examples in MList on a very simple classifier. And you can see that there is no ad hoc way to choose C in general. Like it's very different for different examples. And even for the same model, but non-adversarially trained and adversarially trained, it's also different, which makes sense because a robust model is more robust. So you need to have a higher weight for the misclassification constraints. And lastly, but that's kind of a non-issue, but still, at least it was before, it can be susceptible to the scaling of F. But there are solutions now to that. And examples of that, there is Carlin and Wagner, EAD, which is basically the same, but for L1, Perkel, which is, again, the same, but for, it's Carlin and Wagner, but for color difference, LPA, again, the same, but for LPIPS. There are several attacks that just do the exact same formulation, but you just replace the distance function. So now that we have identified these two families of attacks, that motivated us to do an attack using augmented Lagrangian methods. And that's what we published at ICCV last year. So like I said, the main motivation of this attack was that projection-based attacks are very efficient, but they lack generality, and penalty-based attacks are general, but they lack efficiency. So you want something in the middle. Several attacks proposed for several distances are slight variation of Carlin and Wagner, and they are terrible. Like let's say, like they take thousands of, like tens of thousands of iterations to minimize something that's that you could minimize much more efficiently. And lastly, augmented Lagrangian methods are known to work very well, even in non-convex problems. So so that motivated us to look into that and apply it to adversarial attacks. So instead of solving the argmax problem, which is non-differentiable, obviously we reformulate it. So we minimize the distance function subject to DLR, which is a loss proposed by Francesco Croce last year or 2 years ago, I don't remember. But basically, it's a normalized differential logits, so such that it's smaller than 0, and we add a small positive constant here. It may not seem like much, but like I said, numerical precision in float 32 can be an issue. And if you don't add that, sometimes on different hardware, you get different results with the same perturbation if you get too close to the decision boundary. So to solve this problem, we minimize the quantity, the distance between the perturbed input and the original input, plus a penalty term that takes the DLR function and is parameterized by rho and mu. And the choice of P here is very important. It's what we call a penalty Lagrangian function. And for instance, we have this one, which is very well studied. So you might like that. It doesn't seem, it's not very intuitive what it is. But if I show you these plots, these are 4 very common penalty functions, choices of penalty functions for augmented Lagrangian methods for inequality constraints. So the most famous one is PHR. And basically, it's these functions all have the same kind of shape. They are increasing, and their derivative at 0 is mu. And so if you increase mu, you get a higher derivative at 0. And if you increase rho, it gets the penalty tends to an ideal penalty. So if you take rho, if you take rho very high, you get almost an ideal penalty here. And if you take a rho that's very low, you almost get something linear. So there's this whole spectrum of functions in between, and that's what you use to minimize your problem. So I'll just do a quick presentation of augmented Lagrangian methods for a generic problem and why it works so well. So here we are trying to minimize g of x, and in our case it's the distance function, subject to h of x smaller than 0, and that's our misclassification constraint. And the way it works is, so you initialize, obviously, and then you approximately solve this loss, which is g of x plus penalty of h of x, parameterized by rho and mu. And the approximately here is actually quite important, meaning you don't need to get a very accurate solution. It's not required to reach a very accurate solution. And when you have minimized this loss to some epsilon that you chose beforehand, you compute a new multiplier estimate, and you take the derivative of the penalty. And that choice is actually, I mean, it seems like it comes out of nowhere, but it's actually optimal in the case of strong duality. But and it works even quite well when strong duality doesn't even hold. And then if you also increase rho, so you make it so that the penalty is has a it tends towards an ideal penalty if the constraint does not improve, and that makes your gradient bigger, and it means you have more there is more incentive basically to go to the feasible region. And if it's not converged, you go to step 2 and you start again. And why it works so well is that when strong duality holds, the solution x star and mu star, so the variable that you minimize over and the Lagrange multiplier is a saddle point of both problems. So in the case of a Lagrangian, you have basically a linear term in your penalty. You have your penalty h, and you have your multiplier mu. And for the augmented Lagrangian, instead of having this linear penalty, you have your function p of your penalty, and basically, if you have active constraints, so that means you are in the right the region on the right of the vertical axis. At optimality, you have the same multiplier. So it means that you have the same contribution to the gradients. So the solution is the same, and for non-active constraints, the multiplier mu tends to 0, and that means you also get the same solution. And also, if you know your penalty multiplier, your optimal penalty multiplier in advance, you actually get to the same solution in one minimization, and or one process of minimization, like not one iteration, but one minimization. And the reason also, I mean, the reason we take the derivative is this one. Like if you have your sets of minimizer, so it's the pairs of x and mu that minimize the Lagrangian and the augmented Lagrangian. It means that the derivative with respect to x is 0. If you compute the intersection of these two sets, you obtain this point, and that's your solution. And if you use an augmented Lagrangian method, when you start at this point, You minimize f. That means that you minimize the augmented Lagrangian in X means that you move to the left on the set of minimizer of the augmented Lagrangian problem. And then when you update your multiplier, you move to the set of minimizer of L of the Lagrangian. And you do that again and again, and you eventually you get to the solution of your problem. So yeah, I'm not sure if it's clear, but it's a very good method, basically, to solve inequality constraint problems. And the main advantages of augmented Lagrangian methods are these ones. They are similar to penalty methods. So you replace the constraint problems, but instead of replacing the constraint problem by one unconstrained problem, you replace it with a series of unconstrained problems. It avoids solving the dual problem, which most of the time is infeasible. It yields an optimal weight for the penalty, and that weight tends to the Lagrange multiplier at your solution. And finally, the efficiency of solving the augmented Lagrangian problem solely depends on your ability to solve the inner minimization, so your unconstrained problem, and that makes it much easier to get to a good solution in the end. But in the first, when we tried applying an augmented Lagrangian method, it actually didn't work, or rather it worked, but it was very slow. It was in the context of adversarial examples, it was taking, about the same amount of iterations as Scalini and Wagner, which is exactly what we wanted to avoid in the first place. And that's because of the approximate solving. Like we were solving we were solving our problem with the criterion that was too strict. So we basically relaxed in some way the problem by combining the inner and outer iterations of our minimization. So instead of waiting to approximately solve a problem from one mu, at each iteration of gradient descent, we would update the penalty multiplier. And that means we consider that we have an approximate minimization in each gradient iteration. And in practice, it works kind of well. The problem is that the values of the penalty multiplier you get are very unstable, and they are the one in blue here. And that means your norm, the norm of the perturbation, will also be quite unstable. And just adding some exponential average smoothing basically solve the issue. And you get the solution in orange. It's much more stable, and the same, your norm is stable as well, and you get to an equilibrium between your penalty multiplier and the norm of your perturbation, or the distance in general. And then there are other small modifications that makes it a tiny bit faster and converge to better solutions, but it's more detailed. I mean, stuff that, yeah. And with that, we compared it to several texts, and on a large collection of models that were non-robust, robust, different architectures, and we get these tables basically, and so. Yeah, it's these tables are an aggregation of results on different models, and it's a bit it's like here the median distance is a geometric mean of the median distance over several models. So it's a bit hard to read, in my opinion, these tables, but that's what you need to have in papers today. But I much prefer these kind of curves, which compare the trade-off between the norm of your perturbation and the robustness of a model. So on such a curve, for a more robust model would have a curve that's higher, it means that you need a higher norm to decrease the robust accuracy, to decrease the accuracy. And a stronger attack would have, for the same model, a stronger attack would have a lower curve because it means it can find smaller perturbations such that it induces misclassification. And here are just the curve for the models where it's very different. Because for most models, actually, typically FM and ALMA will have very similar curves, like for most models. There are only on a few models that there are differences. For example, the Cron IBP on MNIST, which has very tricky gradients, very noisy gradients actually, and that a lot of attacks failed. Like for example, FAB, this one like completely misses out because it estimates a distance to the boundary that's not accurate. And for L2, you have same on Cron IBP. You can see that Carlini and Wagner completely fails. It doesn't even find one, I think. It's right at the top where it's basically the original accuracy here. And yeah, these curves also, they have the advantage of comparing different attacks at different epsilons, because most of the literature usually compares attacks at 1 epsilon, and that's kind of a limited comparison since you can tune your attack to work very well for one distance or one specific epsilon, and add a lot of priors to minimize that epsilon specific, to find adversarial example for that epsilon specifically. But if you take into account the whole spectrum, it gets, you start to see differences. Same kind of plots on ImageNet, of tables on ImageNet. Here we see, for example, that L1 is not the best one, for example. It's not the best one on the L1 norm, and it kind of makes sense. Same for the L2 norm against the APGD, because there are other attacks that like I said, the projection-based attacks are very efficient, and for these norms, there has been a lot of research on how to minimize them very accurately. And so that's why the ALMA attack isn't really like the best here, but it's not intended. Like what we intended is that we have an attack that's very general and works well in general, and should be a starting point for minimizing any new distance that you want to attack, and not be and replace basically Carlini and Wagner as a first attempt to minimize one specific distance for example, the CIED or the LPIPS, and that kind of distances, or SSIM or whatever. Again, we can do the same plot, and these plots again show big differences in the cases where you don't look at the median, for example, because when you look at the median on the ImageNet, that would be 50%, and there are only a few examples that are above, like the accuracy above 50% is very low in a way. So that means there are a few examples that you need to perturb correctly to get to 50% accuracy, which is what is compared in several papers. But if you look at the whole curve, you start to see a lot more differences in different attacks. Here you can see that, like, for example, the FMN, there are some examples for which it fails, and that's what we showed. That's what we saw in the table. But on this model, they are basically exactly the same. Like it's the difference is very minor. So yeah, that's about it for the comparison of the attack. And yeah, a complete presentation, a presentation wouldn't be complete without some eye candy. So I did some visualization of the trajectories of the optimization. And I think they show like several things. So here we have the feature space of a model. So it's not the input space of a model, it's the feature space of a model trained on MNIST. So we have a small model, and before the last linear classification layer, we set it so it has only 2 features. So the features are in a 2D space, so you can visualize them without some non-linear projection like TSNE or UMAP or whatever. And here are the trajectories we get for DDN. Then if we add FMN, we get this one. And if we actually compare, the endpoint is very, very close by. And if we add FMN, if we add ALMA to the comparison, this is what we get. So it may look very noisy, and there is a lot of back and forth. And it's actually, it does make sense, because at each iteration, we update the multiplier. And in the first few iterations, the multiplier estimate completely, increases very rapidly because it's the derivative of the penalty. So ALMA completely overshoots at first, and then it will converge to a solution that's on such a small problem. The solution that you get for all 3 attacks are almost the same, like it's numerical differences. And this was for an untargeted attack. So basically the starting example was a 1, and you just want to go to the closest class, which in this case was 4. All attacks went to the same target, to the same class in the end. So it's the 4. So I guess a 1 looks like a 4, at least that's the closest thing. And if you do the same for targeted, you take the attack that's the class that's further, you get this kind of plots. So this is for DDN. You can do the same for FMN, and again the same for ALMA, and you observe the same thing. Basically, the multiplier estimate completely overshoots the target class, and then comes back to a solution and converges to a value that's stable, and it converges on this point here in the feature space. So yeah, that's about it for my presentation. Thanks for listening, and you can find codes of most attacks that I presented on the in my library of adversarial attacks that I try to maintain on a regular basis. And yeah, you can ask questions.
So thank you, really thank you, Jérôme, for your talk. It was really, really, really interesting. So now it's time for questions. So if anybody has one, just unmute yourself and it's time.
Maybe I have a question. Is it okay?
Yeah, sure. Go ahead.
Yeah. So thanks a lot for the presentation. Yeah, it was very nice, very interesting. And so a question about the algorithm. So you mentioned at some point initialization, right? But I'm not sure how this is done and which is the influence, because for many attacks, initialization is very important. Optimization methods in general is important. And I was wondering, like, how influential or it is for the final results, and yeah, if you have some better initialization strategy.
Okay, so you are talking about initializing with the 0 perturbation versus initializing with something random, or another example, for example.
Yeah, exactly. Because you can always add the restarts, right?
So yeah, generally, I don't think, to compare different attacks, making one attack start from random noise is kind of weird, because that means, by luck, you could have a better start for another attack. But maybe you can fix that with the seed, with the random seed or whatever. And also, if you start from like a point that's generated by another attack, that means your attack is not really, like, you're not measuring the performance of your of the attack that you just created. You measured the performance of the union of both attacks, and it's a bit different. From a robustness evaluation perspective, on the other hand, and I know that you are very fond of that, starting from anything is as good as, I mean, if it makes the evaluation, the robustness evaluation more accurate, then yes. I mean, there is no really bad, like counter, there is no really good counter arguments to starting from an adversarial point, let it be another image or something random, if it shows that your robustness is actually lower than what you would have starting from zero. So, but yeah, from the perspective of purely evaluating different attack algorithm, in my opinion, it should start from zero. And performance-wise, we didn't really evaluate starting from something else. And honestly, I mean, we tried just a bit at some point, but it works, like it makes maybe a bit of a difference for non-robust models. But generally for robust models, we found adding noise at the start doesn't change really much. So yeah, that's my 2 cents on that.
Yeah, okay. Yeah, thanks.
So thank you for the question. And any other in the audience? So if you don't, I mean, I'll leave you like some minutes to think about, and I have a question. So I have like 1 or 2 questions. First one is, so at some point, if I did got it correctly, you said, I mean, you use like gradients to compute, but then you need like 1 gradient more. If I didn't get it.
Okay. Yep. It's okay. Here.
Yes.
So yeah, it's just so that the notation is a bit more compact. But the derivative here is not with respect to x; it's with respect to h.
No. Okay.
So you only compute
but...
the derivative of the penalty with respect to h, and that's very cheap. I mean, it's the penalty functions are like they look like that basically. So
yes.
it's very cheap.
Yeah, but so my question is why? So since you're computing like the gradient, you're computing 2 gradients, and then we are in the table of the results, and then you have like all of the gradient computation. I just so the gradient that are computed here are the backwards are just the backward on x, or the summation of the backward on x and h.
No, it's just on x.
So
because the backward, I mean, the gradient computation of the penalty function with respect to h is like orders of magnitude cheaper than computing the backward of the model. Basically, if you compare the runtime of FMN and ALMA, which have the same number of forward and backwards, it's exactly the same.
Okay.
Like there is okay, maybe the difference will be 0.01 second on.
Okay.
It's because all the other operations, I mean, most other operations you are doing in the attack are orders of magnitude smaller than the forward and backward of the model. To the exception maybe of computing Wasserstein, if I'm not wrong, but that's or maybe LPIPS. But even LPIPS, I think it's the model is an AlexNet that you only do forward pass on some layers, so it's still quite cheap.
Okay, sure. Thank you. So we have another question from Maura, and then so I'm gonna do this. So since we are like running a bit out of time, and there are some also like some questions on the Zoom chat and some in the YouTube, I'll take like last 2 questions from the Zoom call, and I'll go to the other questions as well. So please, Maura, go ahead.
Yeah, thank you first for the nice presentation. It was amazing. So I wanted to know two things. One is a quick and easy answer. I wanted to know if you actually improved the evaluation for a Crown EBP model, because that was pretty. It was a tough model to break for me, and I didn't manage to do it when I developed FMN. I wanted to know if the estimate you get is better than the original one.
Okay, so here we are attacking L1 and L2.
Okay.
We don't have an attack for the L infinite, or rather, let's say it's in the works. We have a solution for that. It's soon to be published. But yeah, on L1 and L2, it's that's not what Crown IBP measures. It's for an infinite. So yeah, on that there is no. I don't think I haven't compared actually what we have now. I'm gonna do it.
Yeah, it was just a quick question, and
yeah, it's a very tough model because the gradient is terrible on that.
Yeah, especially next to the original points like of the test set. I noticed, yeah. And also actually FMN really was difficult to improve for that reason. The other question I had is what are the hyperparameters for this attack to work, and also if since this optimization involves a few tricks that are just to speed up and to improve the efficiency of the attack, I wanted to know if you also tried other domains other than images, and if they still work, or if you think they will work.
Okay, so I'll respond to the second question first. There is no domain constraint in the attack, so I don't see any reason it shouldn't work. I actually we have collaboration with the lab in France, and they actually used this attack to attack. By reformulating it a bit, attack a regression model that's on features that are completely arbitrary. So it's not images, it's just features like a vector, and it works. But that makes sense. Just as in FMN or other attacks, there is no domain constraint really. You project back, you have the projection in 0, 1, but that's it's general enough to be several domains. Like audio, I think you can make it into 0, 1, and a lot of things. Like you can rescale and shift in 0, 1, because anyway you have your numerical precision. That means you have bounds on your values. And then the first question on the hyperparameters, there is quite a few. It's because again, it's a matter of what you consider hyperparameter on it. Like some attacks, they say, oh, we don't have any, but you look at the code, there are several things hard coded, and it's that's an hyperparameter. So, but there are several things you can. I don't have them right here. Maybe if I. There are several, but generally we fix them once at the beginning. Like we designed the attack on a subset of basically MNIST to do some quick iterations, and we fixed them and it worked. We didn't change them. The only parameter that we change, depending on the number of iterations, is alpha in our paper. Because alpha is a smoothing parameter. When you have 1,000 iterations, you can smooth with the alpha of 0.9, and that works pretty well because it means the period basically is 10 iterations. So the time it takes to change significantly is 10 iterations. But when you are using the attacks with the 100 iteration budgets, 0.9 is too smooth. So in this case, you use 0.5, and that works. But yeah, it's that's the only one we actually changed in our experiments. For all the rest are fixed. Alpha is, we only changed it from going from 100 to 1,000. All the other are fixed throughout all the models and norms and yeah. And there is, no, actually there is another, but that's distance dependent. It's the initial learning rate, because the gradient of your distance is not always, is not the same for all distances. For example, the gradient for L1 and L2 norms are somewhat well behaved. The gradient for a CIED, the color difference is terrible, because this formula is full of non-linearities and discontinuities, and it's just terrible. So you need to scale that accordingly, and same for LPIPs. So yeah.
Yeah, thank you. So basically, the decision is in the distance you use.
Yeah.
All right. So if you change the domain and use maybe a distance that is specific to that domain, then you will have to probably select one. But yeah, okay.
Yeah.
Thank you. Thank you. That was.
Okay.
Lucas,
do we have space for another question?
Jérôme, are you okay if because there is like one question still from Antonio, one from the chat, which is still there, and then there is a YouTube question. Yeah. If you have time, we can we can ask these 3 questions and then we conclude the Zoom call. But if otherwise, if you you have time constraint, just tell us and we end the stream.
Well, I don't have time constraint. It's okay. Noon and I don't have to go home. So
okay. So Antonio, go ahead.
Okay, thanks. It is really connected to the Mauro's question. So in slide 22, you showed us the evolution of the penalty multiplier, but it was not clear to me why this evolution for the multiplier is jumping so much. So what is the component that make it unstable? So if you can repeat this part, please.
So I mean, the estimation of the multiplier is very noisy, or at least not stable. Mostly it has to do with the fact that the model has a very high Lipschitz constant. Like for very small differences in the inputs, you can have big differences in your logits. And that means that you can, from one iteration to the next, you can go from a correctly classified input, a misclassified input, so your constraint is satisfied. So that means your multiplier will tend to 0. And then the next iteration, your input is correctly classified with even with the high probability, and that means your penalty, the penalty of your the derivative, of the penalty will increase very quickly. So yeah, that's basically the reason. It's like F has very high Lipschitz constant.
Okay, thanks.
And that's the whole thing that makes the optimization difficult.
Hard, yes, thanks.
Okay, so last 2 questions. First, a question from the Zoom chat from Daniel that he says, thank you for the talk. I thought it was very, very interesting. I was wondering if your method would also be applicable to situations where we have discrete, either categorical features over which there is no distance defined? ?
Okay, so sorry, repeat the categorical part.
Sorry. So I was wondering, so also Daniel, if you want to speak, or I'll just repeat the question. I was wondering if your method would also be applicable to situation where we have discrete or categorical features over which there is no distance defined.
It's a good question. I don't think I have a clear, a good answer for that, because it's not specific to my attack, the question, to our attack. It's more, I feel it's a more general question. It's just, it's a matter of defining your distance, and even then if you have categorical inputs, that means you have to handle like a rounding or in some way. Yeah, I don't. We haven't looked into that. I'm not sure how you would be able to apply it to that. But again, I think that would be true for most attacks, if I'm not wrong here. Yeah, it's probably a very different problem.
Okay. Yeah. Okay. So, thanks for the answer. It is a hard problem. So yeah. So
yeah, it's integer programming basically, and
yeah,
that's you need some very hardcore solver for that and a lot of time.
Yes. So, yeah. So last question from the YouTube chat. So I tried to use an image attacking algorithm as a means of video attack. So the model used some time distributed layers, but they couldn't be able to change the model prediction to the desired level. And it was using a Carlini-Wagner attack on a video dataset with binary classification problem. If you have any like suggestion on why it's not working.
Yeah, maybe. It's a bit like that. It doesn't have too many details on the on the problem, but no, I mean the domain is still continuous in this case, and like images is just I don't see why it wouldn't work. I guess Carlini and Wagner is known to fail a lot, so maybe try something else. I don't know. It's it's a bit of a too general question, but yeah. Yeah, I don't see any reason why it wouldn't work, because your input is just a vector in both cases.
Okay.
So otherwise, you should try thousands and thousands of iterations, and eventually it will work.
So yeah, you can take days to attack one video. But,
well, it might be it might be a possibility. If you want to spend that much time, no hard feelings about that. Yeah. Anyway, so the question time is over now. So thank you again for all of the answers, and again thank you for the talk. I'm bringing back the attention to Maura, which wants to say some final remarks before concluding the event.
Yes, first of all, thank you, Jérôme. It was an amazing talk, and especially like interesting questions and answers. And thank you all for being here. And I'll keep everyone posted on the channels we have, Eventbrite, Twitter, and also on YouTube for the next event. Thank you. I'll now stop the streaming.
Oh, thanks.
The screaming.